Now, we need to know more about convex sets. So the final section of this chapter will be, this is chapter 3, right? Some section, it will be more on convex sets. Now, the first result that we will deal with is the following. Now, we know the convex hull of a set, say cap X, is equal to C of cap X, which was the collection of all convex combinations of finitely many members from cap X. Okay, that's something constructive, that's useful, but in Rn, for example, if you take an infinite set, you will also consider all 10 to the power 80 element subsets of that, and you will consider also all convex combination of those 10 to the power 80 members, because 10 to the power 80, well, that's approximately the number of fundamental particles in the known universe. So that's, in a sense, a largest number in some sense, but that's finite. So it would be very nice if actually we could put an upper bound upon the number of finitely many members whose convex combinations will yield the convex hull. It turns out that the number is for Rn, n plus 1, and n does not work. So for that, let's start with the lemma, whose proof I will leave to you as an exercise. Now let I be a finite non-empty set X alpha in Rn and lambda alpha, a non-negative number for each alpha in I. So we take finitely many members from Rn and some non-negative coefficients, and we form their linear combination. Set y equal to the sum of, well, let me put I here. This is finite. Lambda I, xi, I in I. The lemma says if this non-negative linear combination of finitely many members, if this is different than 0, then you can find a subset of cap I, say I naught, which has less than or equal to n members. You take those x bytes which correspond to that subset I naught, then you can find positive coefficients such that y can be written as a positive combination of those members of this collection, but this time the sub-collection that will have less than or equal to n members. Now let's write that. If y is different than 0, then there is some non-empty subset, say I naught, in I, with this I naught having less than or equal to n members. Here n is this n, the dimension of the space, such that there exists a set of positive coefficients corresponding to I naught. This is in 0 infinity now, 0 not included, with y equal to gamma j xj, j is in I naught. So a non-negative combination of some members of Rn that can be written as a positive combination of a subset of those members, but using positive coefficients. Okay? So proof that's left to you. Now we have our theorem, which is due to Koray. Now we take a non-empty subset of Rn. We will characterize the convex hull of this set. But we set Cn plus 1 of x. Here, this n is the dimension here. It's not for any n. This will be the set of all combinations, convex combinations of n plus 1 members of CAPEX at a time. That is for all I from 1 to n plus 1. We have xi in x and lambda I in 0, 1 with the lambda i's adding up to 1. So this is a subset of C of x. When you start with CAPEX and when you form capital C of x, you take any number of members, finitely many, from CAPEX. You form all convex combinations of them. Then you actually throw everything in a basket and you get C of x. So while here, well, there's a restriction on the number of members you take. Cnx, that will be a subset of Cx. Okay. Now the result here is that the convex hull of x is nothing but Cn plus 1 of x. Proof? Well, one direction is easy because C m plus 1 of x, by its definition, is contained in C of x. But we already know that that's convex solid of x. So this set is a subset of convex solid of x. Let's consider the converse. Now, let y be in convex solid of x. But we know this is equal to C of x, so this simply means that there are finitely many members in cap x, one of whose convex combinations is equal to y. Now, there is a finite non-empty set I such that there exist. Now first, xi, I in I, this is in x, lambda I, or let me write here alpha I, in 0, 1, such that sum of alpha i's I in I is equal to 1, such that, here, let me write it here, this y is equal to alpha I, xi, I in I. Since convex solid is equal to C of x. Now, using this lemma, this is a convex combination, but forget about the convex part. This is a linear combination with non-negative coefficients of finitely many members. So this lemma says we can find a subcollection of these exabytes in number less than or equal to n members. Then we can find appropriate positive coefficients such that with those positive coefficients, the linear combination formed, that will turn out to be equal to y in case y is different than 0. But that may or may not do the job because we have no control about the sum of the positive coefficients which will do the job. They may or may not add up to 1. Well, these were adding up to 1, the alpha i's, but now we take a proper subcollection, possibly, of this. We only know there exists just positive coefficients such that y, in case it's different than 0, and if you refer to those positive coefficients as the gamma sub j's, gamma sub j, xj, the sum over the subset I know, that will be y. But who knows to what the gamma j's will sum up. Okay, so let us then do the following trick. Then y that y is in Rn. This is just a real number, 1. So this is in Rn plus 1. This is equal to the sum of alpha i's times xi1 I in I. Does this hold? In Rn, yes. Well, here the first n components, well, that's the sum of alpha I xi's, which is equal to y, and alpha i's, the last component, these are n vectors, this is just 1, the alpha i's add up to 1, that's exactly what we had over here. Okay. Now, we also need not worry whether y is 0 or not. Y might very well be 0. There's no restriction about that. 0 might belong to the convex hull of x. But here, since it's y1, that's different than the 0 vector in Rn plus 1. So by the above lemma, there is some non-empty subset I naught of I with I naught, but now I'm in Rn plus 1 is less than or equal to n plus 1, such that there are or let me write just there is, let me write it as a set, gamma j, j in I naught, this in 0 infinity, such that this y1 is equal to the sum of gamma j's. I take just the xj1s corresponding to j in I naught. But then y is equal to gamma j, xj, j in I naught, and the gamma j's, j in I naught, they add up to 1. And in fact, each is positive. So this actually is now a convex combination of y1. Okay? Does it belong to Cn plus 1? Well, as I naught is less than or equal to n plus 1, well, this might have the number of members in here that might be strictly less than n plus 1. Will it still belong to Cn plus 1 of x? Yes, we can add sufficiently many zeros to that, 0 times, say, one of the xj's. So that will then belong, that will be actually a combination of this form. You take those, well, if the number of terms is not equal to n plus 1, you add sufficiently many 0 times some xj for j in I naught. So that becomes of this form, and its value does not change. Well, by adding sufficiently many, well, if it's less than n plus 1. If it's equal, there's no problem. Many 0 times xj for some j in I naught to the above sum we see that y1 now, no, y now is in Cn plus 1 of cap x. So convex solid of x is contained in Cn plus 1 of x. Thus, they're equal to each other. Completing the proof. Now the question is, fine, that's a good boundary, but could it not be n? Well, here we have used n plus 1, but is it not possible maybe to modify the proof to find some more intelligent idea such that, well, to show that this works also for n? Well, it will not work, and now we'll show by a simple example that this n plus 1 cannot be reduced any further. Any questions so far? Now, example. Now, it will be a simple example to deal with. We consider R2. Now, we let A just a finite, well, x, let me write x, we had x over there. Here, in this case, let us take x as a finite set consisting of 0, 0, 1, 0, 0, 1, and this is in R2. Now let us consider convex hull of x and show that convex hull of cap x contains members which cannot be written as a convex combination of any two of these members of cap x. Now, 1/3 0, 0 plus 1/3 1, 0 plus 1/3 0, 1. This is 1/3 1/3. This belongs to convex hull of x. It's a convex combination of this. Now let's take this and this. For any t in 0, 1, t times 0, 0 plus 1 minus t times 1, 0, that will be equal to, this is t0, 1 minus t0. This, of course, is not equal to 1/3, 1/3. So you cannot obtain this if you just take these two and consider all their convex combinations. Now, secondly, well, the same if we take 0, 0 and 0, 1. This will be, this time, 0, 1 minus t, but that cannot be equal to 1 over 3 for any t since this is 0. So we are left with these two, 1, 0, plus 1 minus t, 0, 1, but that's equal to t 1 minus t. But for any t in here, these will add up to 1, and they cannot thus be 1/3, 1/3. This is different than 1/3, 1/3. So you cannot reduce m plus 1 in the preceding theorem to something less. Okay? Okay. Now, we need, although we had some special subcases of the following, we need to introduce formally the notion of product topology. Now here, we take a whole bunch of topological spaces. Well, they could be infinite in number, but we don't need that. Let's confine ourselves to the finite case. Now, let I be a non-empty finite set. X alpha, tau alpha, a topological space for each alpha in I. Now set X equal to the product of these spaces. So this is just a Cartesian product. Any member X in cap X is a bundle of X sub alphas such that alpha is in I. Now we wish to produce a topology on this product using these individual topologies. Now let's first define the notion of an open set in the product set by using the topologies. Well, let me write open in quotation marks because it will turn out that what we define as open here will form a topology on cap X. Okay? So let me write it like this. Take G in cap X. We say that G is open, quote unquote, with respect to the, well, let me take everything in quotation marks, with respect to, this is just a symbol now, alpha in I, if the following happens. No matter what point in this G we take, for any X in G, But now G is a subset of this, so this will be a member of this form. It will have a component for each alpha in I, and X alpha will belong, lowercase x alpha will belong to this cap X alpha in G. Well, let me write it like this. There is some G alpha in tau alpha for each alpha in I, such that X alpha is in G alpha. The alpha component of this is in G alpha for each alpha. And the product of G alphas, alpha in I, that's in G. So the way, for example, to produce a topology on R2 from the topology on R, according to this, that will be the following. You take some set in R2, you take any X, it has two components, X1, X2 in G, then you should find some open set in R containing X1, some open set in R again containing X2, G1, G2, such that G1 cross G2 is contained in G. So that's just like that. Now, proposition is easy and straightforward to show that the collection of open sets as defined in here, that forms a topology on X. Proposition. Now we have this part. Here. Now, the collection of all subsets of cap X, which are open with respect to this symbol forms a topology on X, which we again denote by the same symbol. And we refer to it as the product topology on X. Now, as I said, it's straightforward, so that's left to you. although it's clear, let me note what I just said. Note. Now let tau be the usual topology on Rn. And tau d, the usual topology on R, just induced by the usual metric, by the distance. Now, tau is the product of tau d's, I from 1 to n. So this does not depend upon I, but it's constant. So you take just the product of the constant. You take tau d each time. Next. Remember in the second or third exercise set, when we considered compactness, now we actually defined some product, some particular product topology there, while on R2, if it's in Rn, well, that A cross B was compact if and only if A and B both were compact separately according to in their own spaces, okay? But if A and B are non-empty, because if one of them is empty, say if A is empty and B is not compact, they're both subsets of R, then the empty set cross any set, that will be the empty set again, that will be compact, but B will not be compact. Take B as R and A as the empty set. The empty set cross R, that will be the empty set, that will be compact, but not both A and B, not both phi and R are compact. But okay, but here we have the following. Due to Tikhonov. Now this again is true for when the index set is for an arbitrary index set, finite, infinite, infinite of any order. But let me write it for the finite cases again. Let I be a non-empty finite set X alpha, tau alpha, a topological space for each alpha in I, and X the product of these. Now, here, of course, since these are all topological spaces, okay, now let me first write. Now, X is compact with respect to the product topology if and only if for all alpha in I, X alpha is compact with respect to tau alpha. Here, since I take these as topological spaces, well, each x alpha will be non-empty, thus x will be non-empty as well. So the problem in the case you consider that will not arise. Now, proof, I leave this as an exercise to you. Now, okay. Well, let me just tell in the remaining few minutes what we'll do in the remaining part of this course. Well, here, well, next we'll show if S is compact, its convex hull is compact as well. That's one. Then we will introduce the notion of affine independence. If in R2 you have P1, P2, P3, 3 points, 3 vectors, can these be linearly independent in R2? No, the dimension is 2, there are 3 of them, they're linearly dependent. But here, this situation with this situation, that is, in this case they are collinear, but here they are non-collinear. There is no line on which they are all located. Now we will characterize, we will distinguish between these, and we will characterize this as these 3 points being affinely independent. Then, using this notion of affine independence, we will define simplices, what a simplex is, and the properties of simplices. Okay? But then, okay, well, I guess that's what we'll do next. Well, then it will be followed by a notion of an affine subspace, which will be a generalization in R1, R2, and R3 of the notions of points, lines, and planes. And that will be the last chapter we'll consider here in this course.